The next couple of classes, we're going to be reviewing the basic types that we use in a computer program to represent values that we're interested in. So these are kind of the building blocks of a program, and then we'll add the structure and logic that makes programs useful. So these are the electrons, protons, quarks, whatever you want to think of it as the stuff that we use to build up a computer program, and it's basically the stuff that a computer program is going to manipulate, that it's going to read in, manipulate, write out, and store in different things. So Python has the following built-in basic types: numerics, sequences, mappings, classes, instances, and exceptions. Today we're going to be talking about numerics, and in the following classes we're going to be talking about sequences. So Python has three basic types of numbers: integers, floating point numbers, which correspond to real numbers, and complex numbers. And so we're going to talk about each one of these in detail following. So the first question might be, why do we need different types of numbers? Aren't numbers just numbers? But if we look at the history of mathematics, numbers arose from two different sources. One was counting, which led to integers with negative numbers and zero added along the way, and measuring led to real numbers. So integers, represented mathematically by the symbol z, are 0, plus or minus 1, plus or minus 2, on to infinity. In Python, in a computer system, we can't efficiently represent an arbitrary large integer, because what we want to do is we want to leverage the underlying hardware of the computer. And the underlying hardware has limitations on how many bytes are allocated to representing numbers. So in Python 2.7, like we're using, the basic integer type integer has a limited precision in that there's a smallest and a largest integer that can be represented. And this is done in hardware. However, to compensate for this limitation, Python also provides long integers, which provides unlimited precision. That unlimited precision comes at the cost that we're now keeping track of things in software and not in hardware. And so there's a loss of computational efficiency with that. So the largest integer that can be stored largest integer value that can be stored is a variable that's stored in the sys module, and it's called the sys.maxint. And on my MacBook Pro, this is the largest integer that can be represented as a type integer on the computer. And you can import system and you can print off the difference. So I'm printing out information about the floating point numbers, which we'll talk about later, and the sys.maxint variable that I just mentioned. So integers can be coded in three different forms. Let me take that back. Four different forms: decimal, base 10, which is the number system that we're familiar with; hexadecimal, which uses a base 16 instead of a base 10; octal, which uses a base 8; and binary, which uses a base 2. These hexadecimal, octal, and binary are really related to the underlying hardware representation in the computer and may not be of use to you in your everyday programming, but just going over this for completeness. So base 10 is the default. So if I type in 10 or negative 27, these are decimal numbers in the same sense that we're familiar with. If I want to type in a hexadecimal number, a base 6, I start by typing the sequence 0x. So if I have 0x followed by something, the computer is expecting this now to be a hexadecimal number. But because we have base 16, we need an additional 6 symbols in addition to the 0 through 9. So we add the symbols A, B, C, D, E, and F as numeric digits to be used in our hexadecimal representation. So here I'm creating a variable A and assigning it the hexadecimal integer value, which I can tell because I'm preceding the number by 0x, 543EF. So I create that variable, and then as I print it, the Python, because its default representation is decimal, is base 10, prints this out as 345,071. So we can see that this hexadecimal number, 543EF, is equal to 345,071. Similarly, we can do base 8 numbers, and these are, we do this by preceding the number by the sequence 0, 0. Now we only need 8 digits, 0 through 7, and so we do not include the digits 8 and 9 in any octal number that we're forming. So here I'm going to print out the value, the octal integer 547, which is equal to 359. And you see this would be 7 times 8 to the 0 plus 4 times 8 to the first power plus 5 times 8 to the second power. Now, if I try to create an octal number with a digit 8 or 9, I'll get an error because I can't form an octal number, which is what the computer is expecting here due to my 0, 0, using the digit 8. Okay, so here now for binary numbers, which is base 2, we create these by typing 0b, and again we only need 2 digits, so we limit our digit characters to 0 and 1. And so I can create these integers. I can do any sort of mathematics with them, so I can create 2 digits here. So here this would be 0 times 2 to the 0th power, so that's 0 plus 1 times 2 to the 1 power, so this will be the number 2. If we look at what b is equal to, this is going to be 1 times 2 to the 0th power, which is 1, plus 0 times 2 to the 1 power, and then 1 times 2 to the 3rd power, 2 to the 2nd power. So that's going to be 4 plus 1, so this is 5. So this is 5 plus 2, which should give us 7. Sometimes I make mistakes and I feel like I have to start the whole video over. Okay, we can take any number that we've defined and represent them in either binary, octal, or hexadecimal form. And here, let me add in different print statements. Okay, so that's basic introduction to integers. Okay, floating point numbers and real numbers. So the idea of what we now refer to as real numbers go back to the ancient Greeks, who discovered that the square root of 2 could not be expressed as the ratio of 2 integers. And so this is where real numbers start. So real numbers can be thought of as the set of all numbers with a finite or infinite decimal expansion. Okay, so the integers are a subset of the real numbers. Rational numbers, which would be 3 divided by 4, is also a subset of the real numbers. But it also includes numbers that cannot be expressed with a finite number of decimals, such as the square root of 2. So how we usually think of real numbers is as a position along a line. And so here's the real number line. We have 0 counting backwards to negative infinity, 0 counting forward to positive infinity. But in addition to these integers, we also have these irrational numbers like the square root of 2, e, or pi, which are numbers that cannot be represented with a finite number of decimal points. What are some of the famous real numbers that would come up in our computing? Well, square root of 2, pi, e, and not really something that comes up often in our computing, but phi, which is used to represent the golden ratio. So the immediate question here, similar to the question of infinite integers, is how on a computer do you represent a number with an infinite decimal expansion? We don't have an infinite number of positions on the computer to represent the values of this number. So the obvious answer is we represent real numbers approximately. And here I've got some links to different issues describing this. So here's on the Python documentation of floating point arithmetic issues and limitations, and a website talking about the perils of floating point. It's important to keep in mind that these floating point numbers are always approximate representations of the real numbers that we're interested in. And because there's approximation going on, we need to be careful because there might be differences that we're unaware of that might make our computer program perform differently than we might assume otherwise. So let's see, that's just printing out some different real numbers. So the math module, which we can import from import math, contains a definition of pi. It contains a definition of Euler's number E, and also different functions such as the square root, which we can use to compute various real numbers. Okay, the third type of basic type of variable in Python are complex numbers. Complex numbers are something that you may never have to work with directly, but are useful for a variety of applications. So I'm primarily interested in medical imaging, where complex numbers are used a lot. Image processing might be an area where complex numbers come up in your applications. So to think of complex numbers, we start by introducing the number I, or J if you're an electrical engineer or you're using Python. And so here, what we mean by the variable I is that I squared equals -1, or that I equals the square root of -1. Now, if you remember learning in math previously that the square root of -1 is not defined. Well, it's not defined in the real numbers because there's no real number that if you multiply it by itself, you get the number -1. But by introducing complex numbers, we can now address this. So the complex number system is the set of all numbers of the form a plus b times I, where a and b are real numbers and I is this square root of -1. So complex numbers were introduced mathematically for their completeness, that all polynomial equations have a solution that is in the set of complex numbers. But they are remarkably useful. And despite their name, the imaginary numbers, complex numbers, it's really very straightforward to think of them as just positions on the plane, whereas the real numbers were points along a line, complex numbers are positions along a plane. And there are different applications, like I mentioned, where they would come up: medical imaging, time series analysis if we're doing things like Fourier transforms, and the frequency analysis of coding regions within a bioinformatics application. So we can construct complex numbers in Python in a variety of ways. We can create them from floats and ints when we use the imaginary part is tagged with a J or a capital J as a suffix. We can form them by passing part of numbers to the complex function, which creates a complex number from two integers or floats that are provided to it, or from a function that returns a complex value. So here's just some demonstration. So just like there is a math module, there is a complex math module named CMath that we can import. We can create various complex numbers, and then we can manipulate them. So let me evaluate this cell of code. So I have created a complex number C, which has no real part. It only has an imaginary part. Complex number is a real part plus an imaginary part. The real part being the x axis and the imaginary part being the y axis. So I can then take a number that has real values like math square root of 2 and -1, and I can pass it to the complex function, which assumes that we're providing two integers, take that back, not just two numbers. If I only pass one number, it assumes that represents the real part. And so here you can see that I've created a complex number 2 with 0 imaginary part as the default value. Having defined a complex number C, that number has an attribute, a real part and imaginary part. And so I can either print the whole number or I can get the parts from it. Okay, what do we do with numbers? Well, we manipulate them. We create expressions and we add them, we subtract them, we multiply them, we do division, we compute the remainders, we might take the exponents of them. So these are the built-in basic arithmetic operators that are available in Python. And here I just created a cell where I'm doing different kinds of arithmetic, and I'm saying what type of number is created by this. So here I'm just doing addition, subtraction, multiplication, division. This is the modulus, which gives us the remainder. And here I'm doing exponentiation. All of these are to be expected, except for perhaps here in this last expression where I'm taking 5 raised to the power 30. Because this number is larger than what can be represented as an integer in Python, it's automatically uptyped to a long integer. So I started with an integer 5, raised it to an integer power 30, but I was returned a long integer, which you can see by the L as a suffix to the number. Okay, Python operators have orders of precedence. If you recall from your high school mathematics, mathematical operators have order of precedence so that we know how to take an expression 5 times 4 minus 3. And this could be, without rules, we wouldn't know whether this should be evaluated as 20 minus 3 or 5 minus 1. From the orders of precedence, we know that multiplication has a higher precedence than subtraction, so we do the multiplication first. So then this becomes 20 subtracting 3, which is 17, rather than 5 subtracting 5, I guess that should be multiplied by 1. Let me just fix that right here. Okay, so if we have two operators, and I have here a link to the Python documentation about precedence. Multiplication and division have the same precedence. In that case, things are evaluated from left to right. So in this case, it will be 5 times 3, which will be 15, divided by 2, which will give us 7, because in Python 2, we have a truncation that's associated with integer division. In this case, we'll have 5 divided by 2, which will give us 2, multiplied by 3, which will give us 6. Okay, what happens when you mix types? So basically, if we have mixing types, Python is going to upconvert everything to whichever representation requires the most number of bytes. We can explicitly convert between types by integer floating point operators. There is a rounding function, and if let's just evaluate some of these. So we started with an integer 5. We pass it to the function float, which returns the number 5 as a float. In this case, we're taking 5 divided by 3, which will be 1. We're adding 0.5, so we have 1.5. This is a floating point number. And then we're converting it to an integer, which drops off the decimal component of the number to give us 1. Here we are taking 5 divided by 3, which will give us a floating point number, and then we're converting this to an integer. So to appreciate why we have a 2, 5 divided by, we need to see what the rounding behavior function is. And you see 5.4 rounds to 5, 5.7 rounds to 6. So we have 5 divided by 3, which will round up to 2, then that's converted to an integer. Python comes with comparison operators. So we have, if we want to say, ask, is one number equal to another number, we have to use the double equal sign. So this will be a frequent source of mistake for you. So the double equal sign means comparison, whereas a single equal sign means assignment. Not equal to is an explanation equal, less than or equal to, greater than equal to. So if I try to assign, this will give me an error, because this doesn't mean is 5 equal to 4. It's saying set the literal 5 to the value 4, which is impossible in Python. Can't assign to a literal. What I really wanted to do there is ask, is 5 equal to 4 with the 2 symbols, and that is false. There's some important numeric libraries to be familiar with: math, cmath, and random. Random generates various pseudo-random number generators. We can find out what's the content of each of these by importing them and using the help. So the help will tell us everything that Python has stored in terms of a help documentation about what's in this module. So it says what the module is, it gives the descriptions of the functions, and we could get the individual description of each function by having done help math.tan or math.tan-h. We can do the same thing with the complex math library. And we can do the same thing with the random library. Where this is describing the different ways that Python will let us generate random numbers. Okay, it's kind of moving on here. Just some of the different random numbers, and you play around with this to discover the different behavior of these functions. There are some more esoteric numeric modules that you might be interested in knowing depending on your application. A decimal is a way that allows us to have floating point numbers with fixed precision. For example, if we want to have 2 decimal points for representing currency. And then also the fraction module, which it provides exact representation of rational numbers. So here's just some demonstration of that. Okay, and then finally, to wrap up, I want to look at NumPy. Now, NumPy is not part of basic Python, so it's a third-party package. It is already installed in Anaconda, so we don't need to do anything extra to make it available to us. But NumPy is essential for any sort of efficient computation with a large collection of numbers. And so NumPy, for much of what we will do, will be as integral to us as numeric floats and integers that we've talked about so far. So we get this package by importing NumPy. It's very common to rename the package as we import it. So here we're going to import NumPy as NP, just to shorten it up a little bit. And so now these variables, these NumPy definitions will be available to us through the name NP. So NumPy arrays are collections of numbers that can be manipulated efficiently. So this efficiency comes by requiring us to both tell, when we create it, what type of numbers they're going to be and what the size of this array that we're going to be working with is. And so this is quite different than most things in Python, where we don't worry ourselves about that. So in NumPy, there are the following types of numbers that we can represent. We can represent unsigned integers with 8 bits. We can represent unsigned integers with 16 bits, unsigned integers with 32 bits, or unsigned integers with 64. And similarly, signed integers with 8, 16, 32, or 64 bits. Now this unsigned and signed, it gets again down to the underlying computer representation, where we need a bit to represent whether the number is positive or negative. And so if we're taking a bit to represent whether a number is positive or negative, that's one less bit we can represent a numeric value with. And so the numbers that can be represented with an unsigned integer, the positive numbers that can be represented, are larger by a power of 2 than can be represented with a signed integer. Okay, why do we want to concern ourselves with these different types of numbers? Primarily memory allocation. If you have a very big array, memory constraints might come into play. If I'm requiring that I use 64 bits, that is 8 bytes for every number, and I have an array of millions or possibly billions of numbers, then what I want to do is I want to use the smallest number of bits to represent the number that I can. So for instance, in image processing, I might have a mask, which is just 0 or 1. So I wouldn't want to take 64 bits to represent a 0 and a 1 when I could get away with representing them with an 8-bit. That being said, there's a computational efficiency in that depending on your architecture of whether you have a 32-bit machine or a 64-bit machine, the basic underlying numerics are represented either with 32 bits or 64 bits in hardware. And so if we have our representation match what the underlying hardware representation is, we have improved efficiency in our computation. And so 64 bits, while they take up more memory than 32 bits, on most modern machines are more efficient to work with because our computers have a 64-bit representation of integers. Okay, so this just shows how we can create arrays and we specify the type. In this case, the size is implicit from the number of elements that I pass to it in this list. And now I'm saying to represent them as integers or unsigned integers. And there's a similar collection of floating point and complex numbers. All these arrays have an attribute number of dimensions and also the shape. So for the ones that we've created, so our variable b is a one-dimensional array, and the shape is 2. So there's 2 elements in that one dimension. We can create arrays with more dimensions. Just kind of showing that here. So you can see like the default type when I provided just integers is to use integer 64. Here I'm creating a 3-dimensional array and doing that with the A range, which we'll talk about these in more detail when we talk about Numpy. But so we've created 1, 2, and 3-dimensional arrays. Arrays can be added together. We can do all the mathematics on them. So if we can do exponentiation of the elements in D piecewise. We can also add arrays together under the caveat that they have the same shape. So here I'm going to take D, I'm going to square every element. Here I'm going to take D, square every element, and add it to the original array D. And here I'm going to try to square each element in D and add it to C. So let's see what happens. Okay, the squaring each element, that all works fine. We can square the elements and add them together. Again, this is our resulting array down here, 3-dimensional array. Everything's happy. But when we try to add the arrays D squared and C, we get an error because D has a shape 3 by 3 by 3, and C has the shape 2 by 2, and so they cannot be added together because they do not have the same shape.